Hello, these are notes for worksheet number 4 for acids and bases. Dissociation. Breaking up is hard to do, but ionic compounds love to do it. It's called dissociation. Examples: you put acid in water, it breaks up into the H parts and the Cl parts. Take calcium hydroxide, it breaks up into the Ca parts and the 2OH parts. And how are we going to use this in a problem? Here are two problems. Find the pH of a 0.01 molar HCl solution. Let me get my pen ready. And let's change the color. The red is a little obnoxious. Do the yellow. So what you need to do first is go HCl. When it breaks up into one H and one Cl part, and its equation is all balanced. So if that starts out as 0.01 molar, that means that's 0.01 molar because there's one of those, and that one's 0.01 molar because there's one of those. So to find the pH, all we care about really are the acid parts. We go pH equals negative log of the concentration of H plus. So we're going to go negative log of 0.01, and that equals 2.0, and that's the pH. Now let's do a different kind of problem. This one is the base. So find the pH of 0.05 molar calcium hydroxide. So first of all, what we want to do, we want to take calcium hydroxide and split it up. When it breaks up, you're going to get one Ca, which is a 2+, and two OH minuses. And what we really care about are the two OH minuses. So if we have 0.05 molar here, an extra 0, what we have here on this one is actually 2 times that, because you have twice as many when it breaks up. So you go 0.05 times 2 is 0.1, how many sig figs? 1 molar. So now to find the pH, we're going to start with the POH, because we don't have any H's. So POH is going to be the negative log of the concentration of OH minus. That's going to be the negative log of 0.10. And that POH, I'm going to write POH again, equals 1.0. That's not our answer, though. We want pH. So pH is going to be 14 minus the 1.0, which is 13. So our pH is 13. It's very basic, which makes sense because we are dealing with a base. Indicators. Indicators are used to detect by changing colors different pH values. There's some examples. There's phenolphthalein. There is pH paper, and there's litmus paper. Make sure you know about these. I do ask test questions on these, so read over them. And then you can use a pH meter. Titration. It's a process to find the concentration of something that we don't know by using a solution with a known concentration or a known pH value. We use indicators to do this. The known solution is placed in the burette. The burette is the glass tube. Your burette in your 5% vinegar lab is the pipette. And the unknown solution is placed in the flask with some indicator. And there's the flask down there. And you used a well plate. And in that well plate, you place the vinegar, which you were trying to find out if it really was 5% vinegar. And you keep adding the unknown into the known, the known into the unknown until you reach a faint color. In your lab, you want the faintest pink possible. Here's some titration simulations if you'd like to watch them. Equivalence point is the point at which the acid parts equal the base parts. Sometimes that's a pH of 7, and sometimes it's not. It depends on the strength of the acid or the base. A neutralization reaction, an acid plus a base is a salt plus water. And here we have hydrochloric acid plus sodium hydroxide yields table salt plus H2O. Note that salt is not always a table salt. It's a cation and an anion hooked up. Titration practice. This is on worksheet number 4, and this is problem number 5. It really is just another stoichiometry problem. There's nothing new other than the word titration. So what we want to do is take the equation. We're mixing sodium hydroxide, NaOH, and nitric acid together, and you will have to figure out the rest of the equation if you want to be successful with this. And you're going to get the salt, and acid plus base is a salt plus water. So you get NaNO3, nano, plus water. There's our water. And now I'm going to write my values underneath it. We have 26.5 milliliters of this, and the milliliters are not going to help us. We want to put that in liters. That's going to be 0.0265 liters, but the molarity is still 0.020. So that's the molarity, and that's the volume. And what else do we know? We have 50 milliliters. Let's put it in liters, 0.0500 liters of that. And we are trying to find the concentration, which is molarity, which is going to be moles divided by liters. Now, if you look at this, we already have the liters, which is good. It's simply what was given to us. We just need to find the moles. Finding the moles is pretty much what every stoichiometry problem is about. So step one, we're going to go molarity times volume to get moles, since we were given those two things. And we're going to go 0.020 moles per liter, molarity is moles per liter, times the volume, which is 0.0265 liters, and that equals 0.0053 moles, and that is NaOH. I'm going to take a shortcut here. I'm going to do step number 2 right here. We're going to do the mole ratio. Just take that number, and we know that there's 1 NaOH for 1 HNO3. I simply looked at the coefficients in front of those substances, and it's a 1-to-1 ratio. Let's look at it. It's a 1, because it's balanced to 1 of those and a 1 of those. Ooh, that's an ugly one. So that means that the number is actually the same. So 0.0053 moles of HNO3. So our third step is to find, or to answer the question. Molarity is moles divided by liters. And we have the liters. It was 0.0500 liters. And the moles we just found 0.0053 moles. And we do a little calculation, a little dance, and we get a number, 0.11 molar HNO3. And that is our final answer. Ta-da! Enjoy doing worksheet number 4.